And we're back. I have my calculator out, and you should get yours out to either real or virtual. I think everyone by now should have access to the Chromebook calculator that TI is letting us use. I know my students. There's a link on Schoology. If you have Mr. Grimm or Mrs. Rawson, I'm sure that they've made that available to you here, and you really do need it for what we're about to do. The good news, though, is that the calculator is going to do a lot of the heavy lifting for us. The real puzzle is applying the correct interpretation to our results. So here we go. So let's look at this example of 58 Hoover High School students. We took a sample and looked at their heights. The sample has a mean height of 68.2 inches with a standard deviation of 3.8 inches. This was all from the sample. And we want to find a 95% confidence interval for the mean height of all students at Hoover High School. There are 4 pieces of information that you need. The size of the sample, which we call n, how many students were in the sample. Yep. What was the mean of that sample? And the standard deviation of the sample, S. Okay. And then the last fact is that it's a 95% confidence interval. Okay. So these are the facts that we need to estimate the mean height of all students at Hoover High School. So to the calculator, first of all, turn it on if you haven't yet. Hit the Stat button and arrow over to Tests. You want to go down to option 8, which is T interval, or you can just press 8 on the keypad. Now we'll talk about data and stats. We'll talk about the data option in a second. For the moment, arrow over to stats and press enter. And we'll start to enter in the results of our sample. So I'm going to shunt this to the side so that you can see it. The size of the sample goes here under N. The mean of the sample goes here. And the standard deviation of the sample goes right in the middle at SX. So the mean of my sample is 68.2. The standard deviation was 3.8 inches. There were 58 students, and this is 95% confidence. Confidence is always expressed as a decimal, and then you just go to calculate, and it churns for a second, and it will give you your result. Okay. 67.201 to 69.199. Okay, so this right here, this is my confidence interval. This tells us that the mean height of all students at Hoover High School is between 67.201 inches and 69.199 inches. Now let's just round that and say 67.2 to 69.2. The mean height of all students at Hoover High School is somewhere in this range with 95% confidence, and we'll talk about what this means in a second. But this is our result. This is what we have been working towards since after spring break. We just used the result of a sample to draw a conclusion, to make an estimate about a population. Now, every confidence interval has a lower bound and an upper bound. The mean of your sample is always in the exact middle of that interval because the interval is constructed around the mean. The difference between your sample mean and the edges the bounds of the interval, and it's either bound, left bound or right bound, is called the margin of error, which is a phrase that you may have heard before. In this case, my margin of error is essentially 1. If you take your sample mean and add 1, that's the upper bound of the interval. If you subtract 1, that's the lower bound of the interval. Our population mean is somewhere in this range with 95% confidence. Let's do another example, and instead of me reading this to you, because I'm a C- reader, I'm just going to have you read it to yourself. And remember that we need 4 pieces of information. What's the size of the sample? What's the mean of the sample? What's the standard deviation of the sample? And what confidence level are we looking at? Okay. So I'm going to go, once again, hit Stat, go over to Tests. I want option 8. I'm going to enter in this information here, which you see here. The mean of my sample is $107.05. Standard deviation is $28.10. I looked at 61 hotel rooms, and I'm looking at 99% confidence. Let's calculate that. I'm going to churn for a second, and there we go. Now the calculator did a little bit of weird rounding here because it ran out of room on the screen. Let's round this to $97.48 to $116.62. This is saying that the mean single room hotel rate in Phoenix is between $97.48 and $116.62. That's a margin of error of $9.57. To find the margin of error, take either bound, lower or upper, and subtract the mean. Make it positive, because margin of error is always a positive number, but it's from the mean to either bound. Okay? And this is with 99% confidence. So let's talk about interpreting precisely what this is saying. Any number in this range is a reasonable value for the mean of the population. So I'm not only saying that the mean, in this case, the mean hotel rate is between $97.48 and $116.62. I'm saying that any number in that range is a reasonable value for that mean. So if someone were to say that the average rate for a room is $105 a night, that would be a reasonable thing to say. With some caveats, I'm starring reasonable, and I'll talk about what I mean here in a moment. But using the result of my sample, this is a reasonable statement because 105 is in the interval. Okay, that's easy enough to understand. This next idea, some people have a hard time with. If someone else were to say no, the average rate is 98 a night. That is also reasonable because 98 is also in the interval, and it is just as reasonable as the first claim. Any value in this interval is an equally plausible value for the mean of the population. There's no statistical difference between these two claims. They are equally valid. Yes, one is closer to the mean of the sample, but that doesn't matter. Any number in any value in the interval is a reasonable value for the mean, and there's no difference. Okay? Now, if someone else claims a number that's outside of the interval, like 120, that is not a reasonable claim according to my sample. What's crazy cakes about this is this could be the truth. This could be true because my sample could be one of those oddballs where the mean ended up just being low for some reason, but at least with the information that I have in front of me, this is not a reasonable claim because it is not in the interval. Okay, so that's kind of the first step of interpretation. Any number in this interval is reasonable. All numbers are equally reasonable. Numbers that are outside of this range are not reasonable. Okay? I'm not saying anything about truth because I can't do truth, because if I knew the truth, I wouldn't have to do any of this. I can only say, using my sample, what's a reasonable conclusion. All right? Now, what's the deal? Why am I hedging so much about reasonable? Here's the thing. Every confidence interval is the result of a random process. Because I have a sample, from that sample I take a mean and a standard deviation, and I use that to generate a confidence interval. So the interval itself is the result of a random process, and as we've seen, and as you know, just out of crazy random chance, you could have a sample that is unrepresentative, that has a mean that's nowhere near the mean of the true population. To help control this randomness, there's a probability attached to how we got that interval that we refer to it as confidence. We don't call it probability because we can only talk about probability in terms of future events, in terms of predictions that of things that have not happened yet. Or sometimes we can talk about how likely or unlikely an event that has happened was. But in the best mathematical sense, probability is used to help predict the future. Once I have a sample, I don't have any more probability because the random part is done. And everything else that follows from that sample is a mechanical process with no probability attached to it. The probability is in what kind of sample did we get. And so we use these wiggle words to avoid confusion. Instead of calling it straight up probability, we call it confidence. All judgments about reasonableness come with this caveat: reasonable with 99% confidence in the last example, reasonable with 95% confidence in the first example. That our confidence level influences our claims about reasonableness. Great. So what does confidence mean? Does our interval contain the mean of the population? Well, maybe it does, maybe it doesn't. I don't know. It depends on how good our sample is. And we don't know. If we knew how good our sample was, the only way to know how good our sample is to know what the mean of the population is. And we just have no way of knowing. If that's why we're here. So maybe our sample is good, maybe it's not. Maybe the confidence interval that we got from it actually has the mean of the population in it, or maybe it doesn't. This is what the idea of confidence is trying to control. Confidence is how we get a handle on this uncertainty. 95% confidence. Now, guys, this has a very particular interpretation, and you really don't have a lot of wiggle room here. Okay? If you look at all possible samples that you could take from your population, 95% of them, if you went through the process of generating a confidence interval, they would give you a confidence interval that contains the mean of the population. You would get a quote-unquote good confidence interval from 95% of all possible samples that you could take. We have no idea of knowing if our particular sample is one of those 95%. We just don't. But 95% of samples do, and we cross our fingers and hope that ours does. Okay, and that's, guys, honestly, that's the best we can do. Now, to kind of show you how this plays out, I wrote a program that does kind of what we did on the spreadsheet. We look at the rolls of 6-sided dice, and from probability, I know that the mean of that population is 3.5. I wrote a program that took samples of 40 rolls of a dice. It constructed a 95% confidence interval from that sample, and then it just generated 10,000 samples. And we could see how many of those samples actually had a confidence interval that contained 3.5 and how many didn't. And the result is that around 95% of them did. Okay? So confidence is a way of stating, how many samples are out there that give me a confidence interval that actually contains the mean. And maybe ours, hopefully ours is one of them, but we don't know. So is more confidence better? Like, is 99% confidence better than 95% confidence? And the answer is sort of. Like everything else in math and life, it's a trade-off. So let's talk about that. But before we do that, let's do one more example with some data. Let's suppose that I randomly sampled 10 cars in the Hoover High School parking lot and looked at their odometer to see how many miles were on the car. The data is on the next page, and we are going to construct a 95% confidence interval. Now, because we are working directly with data, how we do this is a little different. One assumption that we do have to make, though, is that our whole population of all cars, that it is normally distributed. And we need that because we have a small sample size. It's less than 30. Without this assumption, we couldn't do anything. So what I'm going to do is turn on my calculator. I'm going to hit Stat, hit Edit. I'm going to choose a list. Now, if you have things in one of your lists, arrow up to the top, hit Clear, and then Enter, and that should clear out the list. Do not arrow up and delete. If you arrow up and delete, you'll have to go and reset, which is second plus and reset, to get that list back. Okay. Okay, so let's just enter these in. Now these are all one list. 76099, 74892, 497667, 80007, 69414, 47769, 94072, 50904, 67735, 74492. Okay, let's enter these in. Now, I'm gonna now that this is in a list, I'm gonna hit Stat. I'm gonna go over to Tests. I'm going to choose option 8. And instead of stats, I'm going to choose the data option, because that will allow me to choose a list. Now, I entered everything into list 1. If you used list 2 or list 3 or whatever, that's fine. Just go down here and just choose 2, 3, or 4. It's second, and then 1, 2, 3, 4, 5, or 6. So like second 5 is list 5. I want second. I want list 1. Don't worry about freak. Just keep it at a 1, and we want 95% confidence. Hit calculate, and it will take the data we've entered. It will I've clearly mistyped one of the. You know what? I'm just gonna press on. I clearly mistyped something. Maybe you caught it. But yeah, something's off. I'm not gonna. We'll just press on. Here's my interval. The calculator does give us the mean and standard deviation of the sample in case we need it. The interval states that any claim about the average being a certain number is reasonable if that number is in this interval with 95% confidence. And if someone were to claim something like 30,000 or 100,000, which is outside of both of these intervals, guys, I'm really sorry. This is off. It's late. I must have mistyped something. But we'll just press on. Then any claims where that the average is outside of this range is not reasonable with 95% confidence. Okay. And remember, confidence says that a certain percentage, 95, 99%, of all possible samples will give me an interval that contains the true average of the population. So let's come back to our initial question: is more confidence better? And let's look at an example, and I'll have you guys each calculate a different confidence level, and we'll see how they compare. Take a second and read this, and pull out the essential facts and put them into the T interval option under stats. So the average is 375. Standard deviation is 81. And we looked at 87 households. Okay. Now I'm not giving you a confidence level here, because the confidence level that you use, I want it to depend on your birthday. If you were born from January to April, and I was, use a 90% confidence level. If you were born May to August, do 95%. And if you were born September to December, do 99%. Okay? Hit calculate. Now you're going to have a certain result. While you're getting your results, let's talk about accuracy versus precision. We want our confidence intervals to be narrow, because a small interval really helps us zero in on where the mean of the population is. If we have an interval that's 16 to 19, then anything between 16 and 19 could be the mean of the population. If instead we had an interval that was 17 to 18, we would know, we would have a much more specific handle on where the mean is than with a wider interval. So we want narrow intervals. Narrow intervals are more precise, but we also want high confidence. because the higher the confidence, the more possible samples will that generate a confidence interval that actually contains the mean. And if the interval doesn't contain the mean, what are we doing in the first place? Okay, so higher confidence gives us more accuracy. It gives us more confidence that our interval actually contains the mean. Let's compare these. If we did 90% confidence, we got these results, and I'm relieved that I got them in this example here. Okay. This interval is 28, 29, let's say, kilowatt hours wide. So with a 90% confidence interval, the mean is anywhere in a range of 29 different numbers. With a 95% confidence interval, we get this. This interval is 34 kilowatt hours wide. With 99, it's 45. It's not almost, but it's substantially wider than a 28, than my 90% confidence interval. We don't crank up the confidence all the time because higher confidence gives us a wider interval. The more confidence we have, the wider the interval we have. The more accuracy we get, the less precise our results are. Accuracy and precision are in conflict when we do confidence intervals. You can have, given any specific sample, you can have one or the other, but you can't have both. The way that you get both is you plan ahead and make sure that you have a sufficiently large sample. And there are actually ways of calculating how large a sample you need to achieve a certain level of confidence and a certain level of precision. Okay, but that aside, if we're just looking at a sample, we can crank up the confidence and be less precise. We know less about where it is, but we're more sure that it's there. Or we can reduce the confidence and really try to zero in on where the mean of the population might be, except it might not be there. That's the trade-off. To summarize, and we are overdue for a summary. A confidence interval provides an estimate for our population mean using the results of a sample. The calculator does the math for us. Any number in the interval is a reasonable value for the mean of the population. The confidence that's attached tells us what percentage of possible samples can give me an interval that actually contain the mean. We don't know if our particular sample is one of those or not, but we just hope for the best. Higher confidence gives us more accuracy, but it also gives us less precision. The only way to get both is with a sufficiently large sample, and that, my friends, is that. I'm going to stop talking now because this is long. Have a good one. Bye.